Good afternoon. This is a re-recording of lecture number 2 from August 23rd for all sections. Apparently my microphone went out after about 15 minutes of the 9 a.m. lecture and no sound was recorded after that for either lecture. So let's do this again and post this to YouTube. I want to mention the textbook. I mentioned that there would be a meeting at 12:30 p.m. We have had that meeting. And the website looks like it's going to be activated next week, maybe Monday or Tuesday. Now, don't worry about the fact that we have homework tonight. That's all in web courses. But as for reading the textbook, we're going to have to wait till next week. We should be all right with that, so don't stress out about it. Another thing that I mentioned in lecture, there's a special UCF Astronomical Society viewing tomorrow for Mars and other planets out on the Memory Mall. It should be pretty good. It starts at 8:30, goes till 10:30, but they'll probably be around after 10:30. It's run by students, so go see the closest view of Mars for the next many years because of the ellipticity of the orbit of Mars. It's supposedly very close right now. So go ahead and take a look at that. It's not for credit. It's just something I want to let you know about. Go and enjoy it. The supplemental instruction schedule, I want to reinforce that. 2 sessions on Monday, 9 a.m. and 3:30 p.m. 2 on Tuesday, 2 p.m. and 4:30 p.m. The locations, Monday, first session, Classroom Building 1, Room 109. Monday, second session, Nelson School of Communications, Room 111. Nicholson School of Communications, I should say. Tuesday, first meeting, Trevor Colburn Hall, Room 103. That's the new building. And Tuesday, 4:30 session, Classroom Building 1, Room 119. You'll also see the schedule here on the opening page of each lecture down here in the corner. So you'll always be able to look it up and refresh your memory. And just to reinforce, SI is really good to go to if you can make it, and it does make on average a full letter grade improvement for students that can go to SI regularly. So it's a nice program. For students that just added this section at the end of the week, you can get the syllabus as a PDF on the syllabus handouts page in our web courses area. I want to remind you to register your iClicker through web courses only. Do that as soon as you can, and you'll get bonus points next week if you're registered before September 4th. September 4th is when we start taking class participation points for real. So up until next week, we're going to be doing practice questions and a bonus point for each time that you're registered. So get to that. Some of you have already got your bonus points. Another thing I want to mention to you is discussions in web courses, using them as an effective study tool. When you start a thread like this one, where to buy an iClicker, I want you to type in your question or whatever you want to talk about, and I want you to focus on this option set down below. Every time you start a discussion, I want you to activate threaded replies. So check the allow threaded reply box. I also want you to check the allow liking box, and the reason for that is it helps the discussion, the entire thread, it helps it to be more comprehensible, especially without threading. You never know whose reply is addressed to who. So it can be pretty disorganized in a discussion thread where there's a lot of people posting and asking questions and so forth. That's what makes discussion posts helpful, like a little virtual study group. But without threaded replies and liking, it's sometimes hard to tell what's happening. Another thing I want to emphasize is in your title for the thread up here, I want you to type in something that's very specific. So don't just type in "help me," and I mean you can. It's a free country, but it's not going to be as efficient, unless you identify very specifically what you're asking about. So like, how do I get the acceleration in homework number 4, or question 7, for instance? Okay, so type something in like that, and group discussions will be very, very helpful for you. Okay, that's all I want to talk about for those housekeeping details. Now, I want to get back to the idea of physical science, and I want to start the discussion about our human faculty for learning. And here's a lovely picture of students. They got their nose in their phones, but really it shows you that they're trying to learn something from their phone. And that is very typical of us humans. It's part of our thing, the thing that we do, the quest to find information, to find that which is true. We're not looking for lies. We're looking for the truth in almost everything that we do. And science is one of our ways of doing that. So let's look at some of the classical philosophers and what they taught about the way to recognize that which is true. Here's a typical question: does the truth reside in the thing or only in the intellect? So one is objective, one is subjective. Aristotle answers in this way, and this is a 4-part answer, all one sentence. To say of what is that it is not, or to say of what is not that it is false. While to say of what is that it is, and to say of what is not that it is not, is true. And I like to describe and think about that answer as a question about the existence of something. So it's more of an existential answer. Another famous philosopher and writer, Augustine, about 700 years after Aristotle, said it a little more succinctly. That is true, which is. And that's another existential answer. Thomas Aquinas, however, made a little bit more of a humanistic answer. And he answered in terms of us, the thing that we do. And that is, truth is that towards which the intellect tends. In other words, by nature, our mind, our intellect, tends to seek toward the truth, that which is true. So I always think of it as a mountaintop that every one of us is climbing towards the summit. And different paths up a mountain, different steepness, different kinds of rocks, different conditions. But it's it's the thing we do, that towards which the intellect tends. So let's look at some of the signs of the truth. How do you recognize that which is true? What are the criteria? Well, different pursuits of humans have different standards or signs. And we're going to be talking about the scientific enterprise for most of the for all the semester, really. But there's other things that we do as humans that have their own criteria for truth. For instance, somebody tells you that they love you. They write you a love letter. Is it really true? Or are they trying to fake you out? I mean, everybody wants it to be true. Everybody wants to be loved. And so, we write songs about it. Okay? And the songs that we write describe how we know that something is true in terms of true love. So this is the famous folk song, Barbara Allen, a little quote from that. Court of law. That's another human endeavor. It's different from love letters, different from science. Court of law, very formal and very rigid procedures. Here's a picture of some people taking an oath. I think it's before Congress. I swear to tell the whole truth. I swear to tell the truth, the whole truth, and nothing but the truth. And if you're actually in a federal court, there are rules that govern evidence. What evidence is admissible. So, for instance, rule number 804 contains the exceptions to the hearsay rule. The hearsay rule, if you've ever watched Law and Order on TV or something like that, you know that hearsay evidence is not admissible in a court of law, but there are exceptions. And the first one, the first exception to the general hearsay inadmissibility is a statement under belief of imminent death. That's considered or presumed to be truthful and admissible in a court of law. And that's what we would call a deathbed confession. And the assumption is, as humans, that our intellect tends towards the truth. And that if it's your deathbed, you're gonna stop lying and just say that which is true. And so a statement under belief of imminent death is admissible in the court. It has the presumption of being true. Another part of the hearsay exception is a statement against interest. And this one's a little bit more complicated to state, but it's fairly simple to understand. The witness in their testimony make a statement that is so contrary to their interest, proprietary or pecuniary interest, or a statement that has such a great tendency to expose them to liability, criminal or civil, that the assumption is, or the presumption is, they wouldn't say something like that if it weren't true. They wouldn't make it up. You wouldn't want to incriminate yourself into, some crime. You might want to obscure that. You might not want to make the admission, but if you do make the admission, the court assumes that you're not lying. That you're not one of these guys that confesses to every arson incident in the city, like what you see on television and stuff sometimes. Now, that's in two different realms, the court of law and the process of being in love. But what we're going to be, those are important, but we're going to be concerning ourselves with the scientific enterprise. And one of the things that a scientist will try to do in his quest for that which is true is he'll try to make a prediction of a future state. In other words, where is the space shuttle going to land? Do you know exactly the speed of the space shuttle when it gets to Cape Kennedy, to the Kennedy Space Center, the landing strip, et cetera, et cetera? So we want to be able to make predictions, and we don't want them to be false. We want them to be true. All right? Because if you don't make a true prediction, the space shuttle is going to crash. So you want to avoid that. You want to have something that's true. Now here's a picture from the cover art of the first two editions of our textbook. And I just looked at our website. This will be in our website as well. And I challenged the class to look at this carefully and try to see if they could figure out if there was something unusual. And everybody looked at it for a minute and came to the conclusion that in this picture you can't see where the football is. All right? It's a very complex set of interactions here. Everybody's in the mud, the rain is flying, and all kinds of stuff, but you can't even see the football. But they're acting, this snapshot, they're all acting as if they know where the football is. And they may not, but you can't see it in this picture. It might be somewhere out of the picture for all we know. And look at all the different directions that they're looking, that they're moving. It's a wonderful photograph to think about. Another thing that a scientist might, prediction of a future state, who's going to win the game? Okay, so that's not really a scientific question, but it's a sports question, and it's similar. It's trying to make a prediction of a future state of the scoreboard, of the score of both teams. So making predictions, we want to make predictions that are true. You don't want to make prediction that's false. You want your prediction to be as good as you possibly can make. So in all this, the scientist is observing the world and attempting to answer questions about the things that he sees. And that's critical for understanding of the activity of a scientist, a physical scientist. Among other things, he's looking for a plan or a pattern. Is there a pattern in what he sees? For instance, in the arc of a baseball, the parabolic shape, a lot of people didn't know the exact shape of a projectile like that until Galileo figured it out. Another thing, is there a clear interaction of the physical objects that he's observing? For instance, the baseball and the Earth itself. The curved trajectory of the baseball here along its flight path is due to the gravitational pull of the Earth on the baseball. In other words, it's not going straight, it's curving. What's the future state of the things that he sees? So, for instance, if you start your stopwatch at the instant the ball leaves the baseball bat, down at t equals 0.00 seconds, how long does it take to get to the top of its arc, up at the upper right of this diagram? Another thing you might want to do is present your findings to another scientist. And that's the whole thing you do. You find stuff, you write down stuff, and then you share it because other people want to learn about it. And that's where this equation comes in. This is the equation for the y coordinate. Y subscript f, y final, y subscript final, for an object in free fall. And we're going to pull that apart on Tuesday and pull it apart, put it back together. But yeah, that's what that equation is. And that's a compact way of describing and communicating the state of motion of an object in free fall. Now, the guy that figured out all this is Galileo. He famously made his break in the Western culture of the time by proposing a very specific nature of the truth of physical science. Now let's look at some of his statements. And he wrote a lot, but this is a very famous and very important one. And we've talked about this already. It's from Il Saggiatore, which he wrote in 1620, published in 1623. That means in Italian, the assayer. And the assayer is the person that makes small measurements or fine measurements of the refinement level of stuff like gold and silver. You make an assay of the purity of the gold that you have for making, whatever you're going to make with gold. Like the king's crown, for instance. So he wrote this, and we've already mentioned this on Tuesday. Philosophy is written in this grand book, the universe. It stands continually open to our gaze since the time we were little babies. But it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures without which it is humanly impossible to understand a single word of it. Without these, one is wandering around in a dark labyrinth. And we've mentioned this quote from the first day, and we'll be thinking about it. We'll be doing this. We'll be thinking about the language of the universe. It's going to be mathematical. Matter of fact, this free fall equation here for the y-coordinate, every item in that equation corresponds to a line segment, a rectangle, a triangle, or a trapezoid. So that's, and we've written it down in terms of algebraic symbols, but you could make a similar description of it in terms of pictures. And we'll start doing that on Tuesday next week. Now let's get to Galileo's philosophy of motion. He made a philosophy of motion, especially concerning acceleration and force, that was significantly different than what Aristotle had written. And Aristotle was still quite influential almost 2,000 years after his death. And in the time of Galileo, and matter of fact, Galileo had studied Aristotle when he was in grad school. So let's start with the concept of velocity. And a velocity is the combination of speed and direction of an object. So the speed is the number that you see on the speedometer of your car. But when you're driving 40 miles per hour on Alafaya, just saying 40 miles per hour doesn't tell you the direction. So you might be going south on Alafaya towards Waterford Lakes or north towards Oviedo. To describe the position and the future state of an object, you need both speed and direction. And the velocity encodes that. And in fact, we can, if we do it properly, we can make a prediction about the position at a future time and also the velocity at a future time, if we know the way that the velocity evolves over time. So, for instance, one of these big rockets that takes off at Kennedy Space Center or the Cape Canaveral Air Force Station, those are big rockets, and they're moving in 3 dimensions, and so it's pretty complicated. The mass is changing. They're blasting tons of rocket fuel out through the back end, and then they go upward. The rocket blast, the flames go downward. The rocket goes upward, and the mass is changing the entire time. So its speed is changing, and it's pretty difficult to model. But I mean, that's what we need to do. We want to see how the velocity evolves over time for something as fancy as that, or something as simple as a baseball. So it might be going faster, it might be going slower, it might be changing direction. Now, the fancy physics terms for understanding how velocity or anything evolves over time are these two. We want the equations of motion, and that equation y subscript f, etc., is an equation of motion for the y-coordinate. You could also describe it as time evolution equations. Some scientists use that phraseology. So that formula, y subscript f equals, etc., you call that the time evolution equation for the y-coordinate of an object in free fall. Now, I want to talk about motion in 2 dimensions plus time, and I'll just make a side note here. Einstein's theory of relativity, which is my research area, assumes that the universe is 4-dimensional, 3 spatial dimensions, left and right, and then up and down, and then forward and back. Those are the 3 spatial dimensions, and time is the 4th dimension. Now, we're going to do a little bit of a study here in 2 dimensions, starting with point A and point B. So I asked you to sketch a point in your notebook, any couple of points. And how do you start describing motion between those 2 points? Well, first of all, you've got to put down a coordinate system of some kind, some graph paper. So here's the graph paper. Here's some coordinate axes, x and y. And you could put the origin anywhere you want. I just put mine down in the lower left corner. And then you can decide, well, what does each block of graph paper symbolize? Does it symbolize meters or miles or nanometers or light years or something like that? Well, humans are things of human scale. Meters is the appropriate measure for that, or centimeters. Centimeters are pretty good, and meters are good. So a tall person on the basketball team might be 2 meters, and a small, second or third grader might be 1 meter tall, and a little baby when it's born might be about 0.3 meters. They're kind of tiny. So you wouldn't measure a little tiny baby when it's born in miles. I mean, you could do that, but it's better to use meters or centimeters or inches. You wouldn't want to use nanometers either. Nanometers are appropriate to atoms. Miles are good for cities and things like that. Nanometers are better for atoms and molecules, and a nanometer is a billionth of a meter. So in a meter, 1 meter, there's 1 billion nanometers. That's 1 followed by 9 zeros. Okay, so nanometers are good for atoms, but, they're not good for, cities or humans or stars or anything. Now, light years are good for stars. Light minutes are good for the solar system. It takes about 8 minutes for light to go from the sun to Earth. So the distance from Earth to sun is 8 point something light minutes. And to Neptune, it's more light minutes and so forth. So it just depends on the physical system. So let's assume that we're talking about something on the human scale, and we're talking about meters. Now let's look at the numbers on our graph paper. Point B is at 44,24, and point A is at 8,16. So point A is 8 meters to the right of the origin, 16 meters above. And point B is 44 meters to the right of the origin and 24 meters above. And that lets us figure out a distance and a bunch of other stuff. Let's start with the distance. Go ahead and draw in a straight line segment. This one's dashed. And that's going to be the hypotenuse of a triangle that helps us measure the distance. So here's the triangle that we're going to use. Let me move it out of the way here. And this triangle, the hypotenuse is what we want to figure out. That's equal to the length of the hypotenuse of an 8 meter by 36 meter right triangle. All right, so you use Pythagorean Theorem. And you may say to yourself, Dr. B, why is it 8 meters? Well, 24 minus 16, that's the difference in the y coordinates here. That's 8 meters. And 44 minus 8, that's 36 meters. That's the difference in the x coordinates between point A and point B. So you put them into your right triangle, then you use Pythagorean Theorem. We've done that already. You have it for homework. So 36 squared and 8 squared, and they add up to 1,360, and then you square root that, and you get 36.9 meters. Now the thing about that is, that's the distance between your 2 points, but you might not have that for the actual path of the motion. A crow flying from point A to point B would take that path, but you might have a curved path, So this would be like somebody, strolling. Actually, humans don't walk perfectly straight lines. We walk curved paths like that. So that might be a human path. Here's like a robot path, segmented path, 3 straight line segments. The robot is a little bit left, then he crosses, then he goes back a little bit left again, to get point B. So you could have a segmented path like that. Another thing that we would need is the temporal information. What time is it at point A? What time is it when you get to point B? We would want to know that. So, for instance, it might be 1:22 in the afternoon, 1:22:08 p.m. At point A, and then when you get to point B, 1:22:47. Now, this might apply to the straight line segment path, the segmented path, or the curved path. But whatever path you have, you want to figure out at least the endpoint times. The initial point and the final point. But whatever path you take, the speed might vary. You don't really know about the speed. If all you know is the final time and the initial time, you'll know the elapsed time, but you don't know where on the path it is at any one given time, unless you also know the speed. Because the speed might vary. If the speed doesn't vary, then you could figure out exactly where it is. But like on the curved path, you need a lot more information to figure out where you are on that path. So here's a list of the things that we need, to figure out in 2 dimensions plus time. We need positions and distances in meters, so maybe a little bit of Pythagorean Theorem. We need times and elapsed times in seconds. We need directions at each time. So is it a curved path? Is it a segmented path? Is it a straight path? We need the speed at each time along the trajectory. And that'll allow us to figure everything. That's what, the time evolution equation for the speed and the velocity will tell us number 3 and number 4. So if we know that at each instant of time, or if we have an equation of motion for the velocity that allows us to calculate the velocity at each instant of time, we can do that. And there's a section in the textbook that hopefully we get that activated soon about the tortoise and the hare and how the velocity over time for the tortoise varies just a little bit at the very beginning. But for the hare, it varies quite a bit. And so they would have very different number 3 and number 4 on their list of velocities, or for their equation of motion for the velocities. So let's get down to the definition of the speed. Okay, the speed now is a quotient. How far do you go and how long does it take you? It's the average time rate of the change of position. And we symbolize that delta x over delta t. It's a quotient. Okay, so the distance between the two events, we symbolize that with the symbol delta x. And what that means, the Greek letter delta, the triangle, that's capital Greek letter delta. Delta, D for delta, D for difference. It's a subtraction or difference in 2x coordinates. So, and it's always later minus earlier. So x2 minus x1, that's a difference of 2x measurements. Or it could be x subscript f for x final, minus x subscript I for x initial, later minus earlier. And that tells you how far it goes in the x direction. Now, if you're in 2 dimensions and you're on a slant, then you got to do some delta x and some delta y and some Pythagorean theorem to get the hypotenuse. But sometimes if it's just 1 dimension, delta x over delta t is all you need. So as I said, it could possibly be a hypotenuse. And usually in this class, we're going to measure in meters. Sometimes in centimeters, though, and sometimes in kilometers. Okay, elapsed time between 2 events. That's the denominator of this formula. And that's going to be the difference in 2 clock readings. Okay, so what was the time was 1:22:40 122.08 or 118.08, and 122 or 118.47. So the elapsed time was 39 seconds for the earlier sketch that we had. But that's going to be a delta t, d for delta, d for difference. So it's T2 minus T1 or TF minus TI, final minus initial. And again, that's later minus earlier. If you have some kind of a time ordered quantity like position, then it's later minus earlier. Okay, so some deltas are not for time ordered things, but in this case, it's later minus earlier. So let's actually calculate this. All right, we'll do a fairly simple calculation here. Let's put in what we know. 36.9 for the numerator. And that's not really a delta x, that's a hypotenuse, but and then 39 seconds for the denominator, and then take the quotient, and you get 0.946 meters per second. And that's just a little bit less than 1 meter per second. So that might be about 2.1 miles per hour. A rule of thumb is that 1 meter per second is about 2.24 miles per hour. So this is a little bit less than 1. So, we might have 2.1 or so miles per hour. So, but this is a human speed. You can easily walk 2 miles per hour. It's actually kind of pokey. Most people walk at about 3 miles per hour, 2.5, 3 miles per hour. And 5 miles per hour would be almost a jog, almost a slow jog. So now the distance formula, distance equals speed times time. You might remember that from high school. It's just the average speed formula, but cross-multiplied. All right, so what we're going to do is cross-multiply delta t over to the other side of the equation. So that means we have v delta t equals delta x. And that tells you the total time, or the total distance that you've traveled. Okay, and you're going to need that for the homework as well. All right. Now, your homework, if you haven't figured out already, it's homework 1, and it's activated inside web courses. Now, you don't have to use the textbook website for this homework. Eventually we will be using doing some homework over on the textbook website when it's ready. But for right now, we've got plenty of stuff to do. We can do over in web courses, and you're just going to click, and there are multiple choice and calculation questions, and you'll have 4 attempts. So use it as a study tool. Study with a partner. And this one is going to be due at the beginning of lecture. So for the section 1, the early lecture, it'll be due at 9 a.m. on Tuesday. And for section 2, the mid-morning lecture, it'll be due at 10:30 on Tuesday. Homework 0 is due on Friday night. Okay, so try to get that done. That's the one question. Attendance quiz, and actually, if you get it wrong, don't sweat it, because, as I mentioned before, on Tuesday, the federal financial aid surveillance procedure is basically looking for clicks. So if you click in the wrong answer, for that quiz anyways, you've done all you need to do. All you have to do is click to submit it, and you're good. And just so you know, the homework 0 does not count for your semester grade. It's just an attendance thing. But homework 1 will. So do your best on homework 1. You have 4 attempts, and see if you can crush it. Okay, I'll see you on Tuesday. And sorry about the mess with the audio. Apparently, I knocked the plug out during some gesticulation or something. Anyway, sorry about that. We'll do our recordings normally on Tuesday. See you.